Hello, everybody. Really hope that you can hear me. We had some difficulties with the setup, but it seems that we are all ready to go now. So as probably at least some of you know, we had last week, we had this amazing hackathon where Lithuania's AI Association had organized 4 different exercises or four different problems for the community to solve, and we actually had some winners from Kaunas. Oh, by the way, I should have mentioned that we are in Kaunas today, and we had these winners in Kaunas, and here we are today to congratulate the winners. So could we get the winners come to the stage?
Yes. Since we have some unfinished business from the weekend, we did not receive you folks in Vilnius to get some gifts. So eventually, yeah, so we have some prizes additionally to the prize that you won in YouTube competition. So really nice to see you here. And
thank you.
Yep. So congrats one more time to the winners. And in addition, I'd like to mention that really soon, on the 20th of May, we'll have another meetup, this time in Klaipėda. So we haven't had a meetup in Klaipėda ever before. So this is the first time, and we think it's going to be amazing. And we are doing this meetup specifically on Fridays and a little bit later, 7:30. So all of you can participate and be able to drive from Kaunas, Vilnius, or other cities, and maybe spend the weekend in Klaipėda or in Palanga. So think about it. It's really thought about this one. So it's a really good deal, and we expect a lot of people to be there. So see you in Klaipėda. We'll send all the details to our usual channels on LinkedIn, on Facebook, maybe today or tomorrow. And with that, I'd like to invite Kiril, right? Sorry, Petya. So I'd like to invite Petya, who's going to tell us about NLP presentation. This one is yours, right? Integrated language resources. Yeah. So please come to the stage.
Thank you. So I just stand and speak, right? Nothing special.
Yeah.
Okay. Now officially, hi everybody, and thank you for being brave and staying with us. But yeah, we'll try to optimize our talks. So we decided that, of course, our talks are a work. There is a group that stands behind us, of course, and we are only the presenters. But I would like to thank Thomas and you as his colleagues and students and collaborators for the invitation and for listening to what we would like to share with you. Okay, so now I would like to talk about integrated language resources for knowledge graph construction, and later on Kiril will say a bit more about word embeddings and how we can improve them, possibly even more. Okay, really briefly about us. Just to mention the institute that we come from, Institute of Information and Communication Technologies, and in addition, I'm also part of Sofia University, St. Clement Ohridsky. And I must say, maybe at this point, that I'm a linguist, and we are a group that in which work linguists and also computer scientists. So you will listen more about the linguistic side of the things, about the data, what our experience is on that. And the other thing that I would like to mention is about our infrastructure CLADA, which is a joint infrastructure of CLARIN, the European Infrastructure for Language Technology, and also DARIA, which is more about cultural heritage. So in our country, as in many other countries, it is a joint infrastructure. So our work is also connected with this, and you can just see that really we have other members of the team. It's not just us. The head is Kiril, and you can just see about who works on which of our resources. I will not take your time to introduce everybody in person or not in person virtually, but just to have an idea. Okay, so very brief introduction into the knowledge graphs. In our group, we believe that language resources are very important for various applications. We are aware that nowadays with transformers and all the technology, we can work with a lot of data without linguistic knowledge, with unstructured also data. But at some point, we believe that without the knowledge of the specific language, we cannot go further. I mean, that's our real motto. So types of language resources and their integration. Again, in a brief way, a bit of a focus on the event corpus. Why? Because we want to extract events. We want to extract facts from the data for various tasks. And then a bit about data processing, knowledge elicitation, and conclusions and future work. But I'll try to optimize it. So, of course, you should see this work of ours as a use case. I mean, it concerns Bulgarian, but it is also scalable to other languages as ideas and everything. So our ultimate goal is to construct a Bulgaria-centric knowledge graph. And we believe that not only people have biographies, also the geographical entities, objects, everything has a biography. The events, the documents. And also we try to extract as much as possible from the text as such. But we have to structure it in some way. And here we rely on linked open data and also on knowledge graphs. Just some examples, which are not ours, but in principle, we want the knowledge to be connected, not to have language resources and things here and there, and then encyclopedic knowledge somewhere else, but we want to combine them, which of course is not a trivial task. Here, yeah, you can see the connected knowledge. Mona Lisa is in Louvre, and Louvre is a museum, for example. I managed to find a very funny fact that James has lived in Tour Eiffel, which is a very interesting fact, but maybe it's true, I don't know. And the fact he was born on January 1st and the year there. So this is one way of viewing graphs, of course, and there is another way. Here on this slide, you see FactForge. It is visualization that was implemented in OntoText company, and Kiril also participated in that visual graph. And of course, again, this is Bulgaria, this is Plovdiv, and we can see different connections, not all of them very useful for our tasks, but we can retrieve the useful ones. The architecture for building a knowledge graph, of course, we can crawl data unstructured, but we can also have at disposal some annotated data, linguistic data, and everything goes, has to be structured in some way. And here the ontologies can help us. Here we have schema, org, or June names, but they are also behind DBpedia, there is an ontology. and many other ontologies, upper ones and domain-specific. After we have this linking with ontology, which is, again, not so trivial, we need some knowledge graph deployment. And here we, for example, can have Elasticsearch or GraphDB. GraphDB is, again, implementation of OntoText company, and it is very, very popular. They work for BBC and news media, AstraZeneca, and whatever. So at the end, we want to have something to work with, to curate and to visualize it. Okay, here the most important thing is the picture. We have a text. We have some popular Bulgarian singer from, I don't know, 60s. She's very old now, but she sang in amphitheater in Plovdiv. So we want to extract the knowledge about the world from this sentence, from this fact. So we have the language level and the knowledge level. Language resources, very briefly, we have corpora, we have lexical resources. In our case, we have syntactically annotated corpus, as the same is for Lithuanian, especially in universal dependencies. Many languages are covered, which is very nice. And what is new and not very popular is the event corpus. We are trying to build an event corpus to model types of events and what kinds of participants they have. About lexical resources, we have BTB WordNet. So this is meanings of the words presented by sets of synonyms and relations among these sets. And the Valency lexicon. There are many popular Valency lexicons, for example, for Czech language and for Polish. So we have one for Bulgarian, where the verb equals the event, and we want to see all the participants that are typical for this verb or this event. So it's a verb-centric kind of resource, and we want to use them all. For example, this is example from our tree bank, but behind the syntax, actually, which is not important right now, we want to retrieve what actually happened. We know the subject, the direct object, and everything that could help us, but we need, for example, information that there is a showman that was leading a show. Host. I again forgot that in English they use host of a party. So the host of a party, the party itself, and the name of this host. So we want to get these meanings and also to have some link to Wikipedia and to see that this is a person and the page of this person. So I will not, it is a Bulgarian name of a famous person. Okay, so mapping among lexical resources. As I said, we have on the left Valency lexicon which says some organization appoints some person for some kind of duty. And then we want to have this linguistic information, who is the actor, who is the patient, but again, we want to have the meanings of these words, not only the syntax. And last but not least, we want to get the encyclopedic knowledge. And the same, but in a more structured way, you can see here. So we aim at making links among these resources. Okay, that's good. However, within CLADA, Clarin and Daria, we have to work for social sciences and humanities, different kind of areas, to take their data and to make it searchable and useful for them. And then we come to the question of domains. I'll show you the specific domains in a while. So if we want to have tools that process domains, we have to model these domains, like terminology, like annotation schema, like processing of these texts, and so on. That's why we decided to build Bulgarian event corpus. Of course, you know that in the recent years there are many increasing interest in event-oriented applications. For example, such applications are event detection and extraction, scheme in action, event profiling. So what do we need? Improved language modeling for the language that we use it for. And it became possible because now also cross-lingual and cross-domain methods are also well developed. But also the availability of handmade and or hand-induced data that we can train on. Another motivation, if we have such a corpus, we can also train named entity recognition and linking in a better way, and also event recognition models. Okay, so on the one hand, we could help social sciences and humanities, and on the other, we can construct our Bulgaria-centric knowledge graph that would also help these sciences. What are the specifics here? We concentrated on a rich set of named entities. Yeah, even now we can say that the problem of named entities recognition and linking and everything detection, whatever the task is, it is not solved at all. It is very challenging one. And if you go to another domain, it becomes even more challenging for that. Named entities and also the general concepts and events in the different kind of data, these genres and domains. Okay, so I already mentioned the other things. Let's go into more specific information. First, as an ontology, we rely on CDOC CRM because this is an ontology that is very popular in the GLAM area, galleries, libraries, archives, and museums, and also in humanities. But this ontology is not very elaborate, so we needed to put some information also from FrameNet and to adjust it to our data. For the creation of the corpus, we relied on the inception annotation tool, which was not bad at all for this work. And the models that were initially trained, the implementations are in Spacie, Flare, NLP, and Hugging Face. Okay, so in spite of the fact that in the corpus we had nested annotations, our experiments are on the flattened ones. So the NER task is easier, but the domains in this corpus are more complex. So we decided to see how our state-of-the-art models perform on this data, multi-domain data. Okay, so, and that's it. That is the contribution. We have a good corpus, a good resource in this field. And this corpus can provide insights on annotation scheme, on the model, the language model that we use. We can train different models on named entities and events, and also detect inconsistencies in the annotation process. Okay. So a glance at the multi-domain corpus, because I spoke how complex it is, but I never mentioned what's in there. Historical texts from different periods of Bulgarian history, including the deeds and life of Kiril and Methodius, the founders of the alphabet, let's say the Slavic one. So really the texts are from different diachronic periods. Also, cultural artifacts like church icons, their descriptions, scientific publications, archival documents, documents from ethnography also, and encyclopedic articles from Bulgarian Wikipedia. So it's not easy to make one scheme and to make a corpus, but we have a first version and it will be delivered soon. One bottleneck also to mention is how to select topics from so many information sources. Okay, we want to make a knowledge graph, but we have Wikipedia with a lot of information. How do we know what to include inside? And it's not easy at all, but we have two approaches. The first one is expert-oriented, because we consulted experts from different research institutions, which events, which people are important. And the second one was opportunistic. For example, to select the names of streets in 30 largest cities in Bulgaria, and then to see what names were used. Maybe they are the historic persons that are really have to be present in the knowledge graph at the beginning. Where we are on the event extraction radar. As I already mentioned, we are aware that nowadays there are transformers and models that work with unstructured data and so on. And I gave an example for a fully automatic unsupervised method for extracting event profiles. However, we focus on specific domains, and here two main streams compete. I will call this ACE, maybe it's not called in this way, but to be short, ACE-oriented and MOOC-oriented. The first one focuses on verbs, on events. The second one, mostly on named entities, on the participants. So we try to balance between the two. Of course, we aim to have automatic event extraction too at the end, but first we have to have some good corpus to train it on. So about the annotation scheme, the most popular one is this ACE. It defines an approach in which you can see the following elements: events, triggers for these events, participants, and named entities. Okay, so it's very important to have a trigger of the event. I will not take you in very big details here, but more or less we follow their approach. There are some differences with respect to how we model the names, but on a whole, we follow their scheme. And what does it mean? It means we have a layered annotation scheme. First, named entity annotation, which is again not trivial because you will see we have 16 tags for named entities, and then annotating the events with their roles. Okay, you can see visualization in Inception 2, how it looks like. On the top, there are the names, for example, the person on the first row, and then you can see that in green, he was born, the time where he was born, and where exactly. Of course, yeah, just to know what happens there. And also, here you can connect it to Wikipedia as well. So Inception provides a good environment for connected knowledge. Okay, so for inter-annotated agreement, we did it only for biographical subset of documents, not for everything. And for the named entities, it was easier task, between 0.87 to 1. And for the events, of course, it was a harder task, between, again, 0.87 to 0.91. What we can say here, that names of documents and organizations are more complex to handle than these of people and location. And of course, other sources of disagreement come from the annotation guide, where there is some freedom for annotators to annotate longer or shorter spans of information. Okay, and there is a hierarchy. If the annotator is not sure, he or she can select the more general concept instead of the more specific one. Okay, just you can see all the 16 tags. And yeah, here we can see some very specific for the data, like juridical documents, and like another specific one was doc, various texts, including documents, but excluding these juridical ones. Ref, also bibliographical references, citations, links, and so on. I mean, it's, again, not trivial and not the best one, but it worked well. So basically what I said is here. For example, we use different tags for people, for nationalities and regions, but then for the experiments, we aggregated them because otherwise it's difficult to have something good. Okay, examples of events. The first one is donation. We have the donor. These are the participants, the roles, recipient of this donation, the team, mediator, period of iterations of these donations, the goal, and time and place, which are typical for many, many events. Giving birth, the second one, brought into life, the newborn person. Here we have parents as a role, but also mother and father separately, because sometimes in the text you have the aggregated one or the separate ones. So, and the same for the other events. As I said, we had some experimental setting with named entity recognition, and you can see the how the documents were divided. They were 325 annotating files. We have training, development, and test division of documents. For the experimental work, we compare spaces transition-based approach with FLAIR. And for a baseline model, it is a built-in spacing named entity recognizer. Okay, and you can see the other details as well. Two types of embeddings were used here. Byte pair embeddings that can use subword information. It is good for the unknown words problem. And the other one, the character-based, which is also very popular embedding, it can reflect also the diachronic changes in the data when they happen. Results and evaluation. We can see that the baseline was better on, for example, time for F measure and document. For the others, it was improved, not as much as for the state of art for Bulgarian, but still it is a good improvement on that. So the best detected labels are the locations and person and the aggregated person and events, which is good. The underscored types are juridical, document, and product. Not only because there are not so many mentions of them in the data, but also that the annotation can vary. Yeah, qualitative analysis. The main errors can come from the model and from the data, of course. For example, the model can confuse product and document because books can also be products, right? And we have some more specific label in addition, like document. And also the model might not recognize the specific context. Like we have these nice examples with village Bulgarians. Bulgarians is an ethnonym, but in this context, it is the name of the village, not ethnonym of where we come from. And as I mentioned, handling the nested named entities. So this is briefly just our NLP pipeline for the moment with the standard metrics, but it hasn't been applied on the event corpus yet. And we go to word sense disambiguation, event recognition, and named entity identification and linking. Okay, we go to knowledge elicitation. So what we imagine after we have this knowledge graph and data is how we can extract RDFs, the triples, and using it accordingly as linked open data. For example, this fact, we have to change the fact with other facts that came recently, unfortunately. Great Britain left EU. So we have the annotations in inception. We have the event leaving and who left and what was the organization that was left. And before I show you how it looks like, you can see, for example, the event of leaving as it is in the ontology, and in our annotation schema, it goes to event label. The actor could be person or group, and in our schema, it corresponds to the named entity labels person and organization, and the same for the others. The separation as relation and so on. Okay, so this is the export file for the same event. And from this, we can make RDF, which says exactly this, that Great Britain and Northern Ireland left the event of leaving European Union as a group from there. Okay, so here we show you again a visualization of what we aim at, but in another way of visualizing it. Like if we have an ontology, then we have to connect this ontology with lexicalized items, with our dictionaries, but not only, also with free phrases, you know, from machine translation, maybe that we cannot stop with only words and dictionaries. And then how to project all this into the domain texts that are on the bottom through different kind of tools and grammars. Yeah, and here it is the Clada BG architecture with me on the top, and so I'm very, very happy there because in this ideal world, I will work with the knowledge graph that we have at the end. And when I work with this, I can make some queries to the document database. Of course, I can get more information from there. If I make something new, I can contribute to the knowledge graph and also to the document database. So why knowledge graph? If we have all these things like Wikipedia and DBpedia and geonames and so on. First, because it is really centered only on Bulgaria. Our Wikipedia is not very big. Very often there is no information about anybody, let alone in English one. And the other thing, we would like to have verified facts from experts in these domains. Okay, so I try to be quick. Some general conclusions and future work. Okay, we are completing the first versions of domain language resources for this graph. We have some initial NLP pipeline for annotation of the domain text in progress, and we started already integration, mostly with lexical resources, syntactic resources, and encyclopedic resources, as I showed you. And we just go on with that. Now we have to integrate with events. And specifically for this corpus, the event one, yeah, it is very good to have a multi-domain event-oriented corpus with diachronic dimension. And not only named entity recognizer task, but also other tasks are not trivial on such a corpus. The results are promising for some labels, for some they show some of the problems and we can address them. We also use these experiments as means for error detection, for reclassification, and improvements of the annotation process. And of course, the corpus will be made available through Eura and through CladDBG repository. And we also hope that within Clarin, some kind of family of event corpora can be enhanced at some point. Also for other languages, as far as I know, there are not so many yet. So that would be nice. And yeah, cited literature in the presentation, and I will just stop here because we are very advanced with the time, and Kiril has to say also something. Okay, thank you. Yeah, I don't know for the questions, if there are any immediate ones or also suggestions, we would be happy to hear them. Yes, please.
So about the event annotation. So you showed some numbers, right? So is it the binary classification in the way that the event is detected or not, or you also determine automatically the class, let's say it's the concert, the conference, and something else. So how, what that value shows exactly?
The second one, I think it is, but let Kiril say more.
For the moment, we don't have yet automatic methods for recognition of events. We just in annotation a few months ago. So what the figures shows in the previous slide.
The previous. Okay. Yeah, actually.
This one.
The
On the table.
okay.
The values.
Okay.
Къде на долу? Ага. Да има values.
Yes.
Okay.
These values So I see the export for Evan.
Yeah,
I
yeah.
understood it's events.
No. I wanted to jump into your answer because I realized what you mean. There is some overlapping because I didn't say. Yeah. We have event annotated at the named entities level already, like the wars or something.
The second floor to war.
Yeah.
It's a name entity.
Yeah,
for the
event.
event.
But
But
there is another layer in addition. I skipped that slide with the comparison with Ache. And then we continue with saying what kind of event it is. So here, it is only that's event. That's why it's so good. But we didn't make any experiments with the second layer.
It is because for the fact extraction, we rely on name entities. The mapping from the name entities to TVP will arrive in the objects because we would like to extract facts about the objects, not general events. So here, for example, the event could be second floor to war.
Yeah, when the event is a name or something unique, but otherwise that somebody left something like with the Brexit, it was not part of this experiment yet. That would be interesting to see how it performs there.
So for the events, we still don't have a good turnover to report. This is why we are not reporting it.
And it also depends on named entities, right? So you need to increase the accuracy there to have good accuracy for the event.
Yeah. It's again, sometimes it's domain specific as well. And there are cases when we were wondering whether it's a name or it's not a name. I mean, these gray areas between, and when we introduced also the terms per domain, it became really complex task. That's why experts after that will check whether it's term or not. We are not good enough on that. Thanks. Yeah. I skipped that slide. And yeah. Any other questions?
How it compares with GDAL? If you look, because there is a big database there, try to extract events from media also and do some annotation. I don't know how much it is done automatically. It's called GDAL. Maybe it makes sense to look at it.
Yeah, it makes sense to look at, yeah.
It's quite interesting. It's in English.
Yeah, but we can see how we can adapt, of course. Thank you.
Here we just, because in the reception, we put within some machine learning modules. So for some of the names, like the personal names and application, it's relatively easy to achieve a good support in the beginning. For some of the text, like the scientific publication, they have quite a specific language. So it's not so easy to put general name entity recognition module. So somehow we stopped with these experiments, but we hope now in Spacey and the environment around Spacey to try to enlarge
English surveys, let's say Macronas, we add the endings, and we also change some pronunciations, making them more Lithuanian. I guess you also have these problems.
No, we are not so Bulgarian centric, but Czech Republic, they do that because I studied Czech language. They really make it sound Czech. In our case, we just, but we have the problems with Cyrillic. We always have problems, with that. So Sophia Loren is Sophia Loren, but in Cyrillic. And sometimes you can have several kind of Cyrillic writing. And at the time, Kiril also had worked on transliteration module just for this problem.
This is just to transfer the words from Wikipedia, English Wikipedia to Bulgarian. So transferring the facts from there. But in Bulgarian, we have some word forms for names, like Kiril, Kirillovci, so it means several people that are named Kiril, but it's very rare.
Good for you. With the start, let's say Biden, it's written absolutely different than we have to say in English. It's one version, and Lithuanian we write absolutely different, and plus we add the ending, and it can be in different cases. So.
Yeah, but for me it's okay because I already know such an approach, and I like it. I like it actually. It becomes Balto-Slavic. Okay, any other questions? Thank you for the comments. Okay, if not, maybe you can continue because Тай казвай само важните неща, защото много пренапред.
Колко часа?
Ами,
8 часа.
иде.
Everything should work automatically, just as soon as you change. Give me a second to check if everything's still fine. Yep, looks good.
Yeah. Thank you. So first, thank you for the invitation and for giving us this possibility to present our work. Here I will tell you about some experiments we did for using linguistic knowledge and also some kind of linguistic knowledge graphs to improve word embeddings. So first, a few words about distributional semantics, which is behind the word embeddings as such. Then a little bit about word-to-vec architecture and some others. Word sense disambiguation as motivating task for the improvement of the how we improve the word embeddings. Generation of pseudo corpora, which in fact we are using for improvement of the embeddings, and some conclusions in future work. Okay, so the distributional semantics is a huge research area. It started almost more than 60 years ago, in fact, which is trying to study the quantifying and categorization of semantic similarity between linguistic items based on their distribution properties in a large sample of language data. And one of the motivation for this work is this expression by Firth, that in order to recognize the word and characterize it is to take a look in the context of usage of the word. So on the base of this, a lot of approaches in distributional semantics were developed. Like a modeling, they rely on the linear algebra as a computational tool and representational framework in which the information for the semantics of the words are represented as vectors, and different manipulations and measurement of the similarity and the usage is done also via linear algebra methods. Distributional information is represented in high-dimensional vectors, and the similarity between the vectors usually represent different kinds of similarities that can be found in the context, like topical similarity, the different topics in the different texts, or paradigmatic and syntagmatic similarity depending how the words are used in the text. Different methods that already exist for many years, just mentioned here, like latent semantic analysis from 80s, hyperspace analog to language, syntactic independency based models, and some others. And in how the different models in distributional semantics differ. So what the different parameters play roles. First, the context type, whether this is some kind of textual region, just the window around the words that are interesting, or some linguistic items like dependency structure over which the similarity is checked, or even more complicated analysis like lemmas in lemmatizer or word sense annotation. The other parameter is the context window, the size of the context in which we could measure the impact of other words on the word that we are considered, the frequency, weighting, like entropy, point-wise mutual information, dimensional reduction. At the beginning, each of these vector is representing one with one hot vector, so one value for the different elements that are classified, and then different ways to reduce the dimensionality of the vectors. Like the most popular one is singular value decomposition, and also some others, and similarity measure, which the most popular one is cosine similarity, but also can use other distances for this task. Word embedding is a relatively new method, which is using for language modeling and also for learning features from the text, and used in NLP task, especially when neural network architecture applied. So word embeddings playing the role of the input and output of the neural networks, where the words and the phrases from the vocabulary are mapped to vectors of real numbers with relatively small dimension. Conceptually, it involves mathematical embeddings from the space from one dimension per word. So these very huge vectors and to reduce to vectors with word dimension. Here I just show how this can be done manually, and for many years it was done in this way, when in fact the feature engineering approach was done. So here are some examples from our resources for Bulgarian morphosyntactic tags. We have 680 different tags in the tag set, and if we need to use this like input for a neural network architecture and encoding like one hot vector, we need for each word a vector with 680 tags. But if we divide the tags in the corresponding information that is represented inside, so for example, we can represent one tag with several vectors, one for part of speeches with 10 positions in the vector, one for gender with 3 positions, and so on. So at the end, in order to represent each of the tags, we have only 27 positions. Okay, similar could be for the inflectional lexicon, where we have something like 70,000 lemmas with a nearly 1,200,000 word forms. And if we need to encode each of these as a vector, we need really a huge vector. But using, again, here the feature engineering, like for the grammatical features, we reduced to 27 positions. So combining with the lemmas, we reduced from 1,200,000 forms to 70,000. And using additionally the semantic categories from WordNet, we can even more reducing more the decimal. So here is another example which I will skip. So the hope behind the word embeddings is that this process of reducing the size of the vectors can be done automatically, also not just by engineering the features that used for input for the neural networks, but also learning some regularities and some features from the actual use of the language, so from the texts. And here is one of the most popular architecture. This is word2vec. They implemented two types of architectures. One is continuous back of word architecture, where we have words in the context. So taking a window here with four words in the context and predicting the word in the middle. So the neural network is predicting from the context the actual word, and this is optimization of the algorithm of conditional probability this word to appear when we have these words in the context, where the embeddings come from here in this architecture is from the matrices, from the input layer to the hidden layer, where each of the row in the matrix corresponds to the embedding of one of the words in the lexicon. Another architecture is in the opposite direction, from one word in the text to predict what are the possible words in the context. And again, the training on a huge number of huge corpora gives us the embeddings for the whole lexicon that is used in the text. What are some of the open questions behind word embeddings? One of the questions is what exactly word embeddings learned from the text. Is just this whether this is just the semantics, like in what is the hope in the distributional semantics, or some other information like grammatical information or word facts. In fact, for English, many of these learned. For example, we can try what is learned in the word embeddings with some kind of analogy. For example, if the capital of Lithuania is Vilnius, and what is the capital of Bulgaria, it has to say, okay, it's Sofia. So this is somehow the world facts about the countries and the capitals. Also some semantic information, something like if something is possible to be done, so this is possibility, and if we have to do something, then it has to say this obligatory to do. And of course, some grammatical information for English, like if we have a table and tables like a plural form, and then chairs, and it's okay, this is chairs. Some of these facts are not so easy to learn for other languages, like for Bulgarian. The grammatical level is very hard, especially for verbs, because we have a lot of verb forms and there is not enough data. Even in a huge corpus for many of the verbs, there is no examples how these verbs are used in the different forms. Another question is with the frequency of the different word forms in the text. So if we have one very frequent verb, not verb, but a word, and one not so frequent, whether we learn the same features for both of them in the word embeddings. And fortunately, sometimes this is not the case. And for some of the applications, like for machine translation and some of the manipulations of the word embeddings for different tasks, we also interesting how to build such correspondences, for example, embeddings from different languages and from different domains. And the question, of course, is how we train word embeddings, and the most popular way is to collect huge corpora, which is not so hard nowadays. So there are so many texts on the web, which is relatively easy to build a corpora with billions of words in them. And the expectation is that paradigmatic and syntagmatic relations between the words in the lexicon can be learned from the texts. And another approach is to use knowledge that is already represented somehow in different language resources, like WordNet, FrameNet, WordNet for the linguistic knowledge, and Wikipedia, DBpedia, Wikidata, and some others for encyclopedic knowledge. Okay, so this is the first part of the talk, which generally just said what are the questions that we would like to address, and how this combined with some of the tasks that we had to decide. One of the tasks was word sense disintegration, so having some kind of sense inventory, like in WordNet, and the task is to assign for each of the open class words in the text the corresponding sense. There are different approaches, which I will not cover here, but of course there are machine learning, like supervised methods and unsupervised, but of course for supervised, which is the best one, the state of the art at the moment and also in the past, you need to have a corpus manually annotated, which is very expensive task to produce such corpus, and this is what Petya said in the previous talk. Unsupervised method, of course, is via the clustering of the senses in the text, but it's not so easy to connect the clusters then with the actual inventory of senses. And knowledge-based approach is using the structure of the sense inventory. So let's say the WordNet with the relations between the scene sets, with between the concepts represented by these senses, and exploit this graph or knowledge graph in order to assign senses in the text. Having this mapping from the graph to the text, there is of course a way to go in the opposite direction from not from the text to the senses, but from the senses to some kind of text, which is called here pseudo text. And in fact, we're exploiting exactly this thing. For the experiments, we're using one system, UKB, which is implemented from the University of Basque Country in Spain. So, and generally, they implemented several algorithms for random walk on graphs, and the most powerful one is the personalized PageRank algorithm, where the knowledge graph for WordNet is constructed like arcs between senses in the WordNet. So here we have the ID for classroom, and then it's connected to school, like part of a relation between the two senses of these words, and some metadata that is saying that this is for the version 3.0 of the WordNet, and the arc is not directional one. So we can imagine that the knowledge graph in this case, it's here in Bulgarian, is something like this. So on the top we have entity, then we have devices, agents, events, buildings, and furniture. So this is one level in the hierarchy, and then we have electronic devices, and then a speaker, like one concept. Then we have agent, which could be organizations on people, and then organization can be party, or the person can be a speaker, or playing the role of the speaker. Then we have events, which is, for example, here entering, and then some buildings, and on this level here we have a canteen, and then the furniture is a chair. I especially select this element because they are
the speaker of the party entered the canteen, right?
Okay, thank you, Petya. I just wanted to say this. Okay, this is selected because in this sentence, the speaker of the party entered the canteen, but it's ambiguous. Thank you. So the speaker could be the device or the person. And here the canteen and the chair in Bulgarian are the same word. So having this and using the dependency information from the syntactic structure, so we have a huge graph that contains the knowledge graph and also the graph over the sentence. Applying the PageRank algorithm, it prefer one or the other senses inside of this graph, and this is how the word sense disambiguation is done. Okay, so when we, in fact, we did also our own implementation of the algorithm just to be able to play with it and to see how it behaves. And we recognize very quickly that adding new knowledge, like inheritance here and some syntactic information, is improving the result. And from here, we decided to not just to go with the WordNet graph, but also to enlarge the graph with additional information. And here is how we did it. So this is the initial graph from WordNet, and here is the hierarchy of nouns, and here are the hierarchy of verbs. And in most of the cases, there is no connection between these two hierarchies in the original WordNet. What is not good because we cannot use the co-occurrences and also the knowledge that usually nouns participants in the events. What kind of new knowledge can be added here? The first one is inheritance. So we can add relations that is in fact transitive closure of the hypernymy relations from surgeon to professional, and here from consult to investigate. Another extension could come from the syntactic information. So when we have a corpus that is annotated with senses from WordNet, applying some kind of parser and see that the doctor is doing some research is mentioned inside of the text. So we can extract this information and add it to the graph, and in this way connect the two separate hierarchies. Then we can inherit this information. So if the doctor can do the research, we can claim that also surgeons also can do research. Of course, we can do some kind of generalization. So from doctor, we can say probably also professional can do research, and then inherit this information from professionals to other sub-concepts like professor. Of course, here is not always the case. So this is not always a good way to make inference, because if we have animals, cat and dogs, and we have information that dogs can bark and generalize, then also cats can bark, what is of course not correct. And another inference that can be done here is from sub-events to more general events. So if somebody is doing research, definitely is doing investigation. Okay, applying all these types of extensions of WordNet, these are the results. So if we use what is already available in WordNet, so the WordNet knowledge graph, and WordNet knowledge graphs with glosses. So glosses like occurrences of the concepts inside of the. We have 51% or 53% accuracy, and then extending with inheritance, we are almost the same, but using inheritance and syntactic information, and also this type of inheritance of the syntactic information and generalization, we improved the results with almost more than 10%. Okay, this was quite good. And we decided to take a look on another source of information for the extension of the knowledge graphs. So we used extended WordNet, which is WordNet with definitions and examples analyzed in logical form. I will show you one example in a while. Then some semantic annotation sentences like restrictions over the graph, and they came from the glosses in the extended WordNet, syntactic information sentences from SEMCOR, which is corpus annotated with senses from the WordNet, and they were added in different ways. So the logical form is something like this. If we have disability and disability like C set with the definition, a word that has having two syllables, then the logical form is represented like this predicates with variables, and from this we can infer some new relations, like have something something that word can have something, and also syllable can be part of the having event, and also between that word has a syllable and to somehow modify syllable. So this is how we extract new relations from this data set, and we code in this way. Okay. Thank you, Petya. So similar with dependency structures, and also with just text annotated with senses. Here is the information about the experiments, and what we can see that adding different kinds of relations here, we receive these results, which at that moment was in fact the state of the art for English. Okay, so how to go for word embeddings from all these knowledge graphs. In fact, applying the random walk on graphs, but in the opposite direction. So going from one node in the word net to another, randomly to another node, we print a lemma for each of the nodes. So like Goldbrick, Duperry, Taking, Gulf, and so on. So this sequence of words resembles to some extent lexical chains in the real texts, without some of the functional words, and also agreement inside is missing. But but in this way we can produce a lot of artificial texts, and also for each of the words inside of the word net, we can produce as many as we would like to have. So this means that what we have as a problem in the real text, that a lot of words are not mentioned at all in the text. Now we have a control how this to be skipped. How to evaluate? There are some data sets for paradigmatic similarity and syntagmatic similarity, which are manually constructed, and we are using this like measurement how good the embeddings are. And here are the results. So like a baseline, we take the Google News and dependency type of word embeddings, which already exist on the web, and this is the correlation between the human annotator and what is predicted by the embeddings. The third row is the best result from the experiments that Basque people did with the UKB system, and the rest is what we achieved with adding different type of relations. And what is interesting here is that when we add more like paradigmatic relations to WordNet, we improve the paradigmatic similarity, and when we add more like syntactic information, we improve the syntagmatic similarity. Okay, so from this, what we can learn for that for the different levels of in fact, the word embeddings, in fact, contains information for the different levels in the language, starting from the grammatical features like plural forms and some others, selectional restrictions of the relational words, semantics, and even word knowledge. For the different tasks, of course, we need different kinds of this knowledge. And the last thing is that using some kind of improvement the way in which we generate the pseudocorpus, the artificial texts, we can improve also the quality of knowledge in the word embeddings. And we will go back to what Petya already showed shown in the previous. So this was one of the motivations to integrate all of our resources, including many types of information. Here on the left, we have the corpora information starting from text, adding syntactic information, and then annotation with senses from WordNet and concepts from Wikipedia in this case, but related to Bulgarian Wikipedia. And also the lexical information, which at the moment includes WordNet, Valency lexicon, and Wikipedia. So using this, we can use all of this information together to produce different kind of artificial texts in order to train word embeddings. What additionally we are working on at the moment, so we extend the Valency lexicon with other relation words, not just verbs, but also prepositions and some nouns and other words. Analytical verb forms vary. So the syntactic part of the verbs is not so big, but analytical verbs forms are very big. So we making some patterns of this and implementing generation grammar to generate the text in a better way. For what Petya shown in the previous presentation, how to approach the domain, the different domains, because in the different domains we don't have so many texts. We extract from the annotation the terminological lexicons that we aligned with the WordNet and use this for generation of artificial text in the domains. Anonymization of the corpora, exclude the name entities, and so somehow reduce the impact of the word knowledge to the semantics that is learned from this. And one open question which was not mentioned is that for some of the verbs, for some of the words, it's important to have not just one embedding, but several embeddings. For example, for verb, not just for the verb, but also for the subject, objects, and such stuff. And here is just one, a few examples. So here is how we are producing more examples with analytical verb forms. So starting from Kiril Kaunas. So Kiril is in Kaunas. We can substitute the verb in the present tense with some special forms, producing sentences like Kiril has been in Kaunas or questions. So in this way, we can show the different forms in the text that usually not appear in the text. And this is how the training for the grammatical roles, for example, for subject objects and indirect objects can be learned. So from syntactically annotated corpus, we substitute the subject with a pseudo word and the objects with pseudo word and indirect objects, and then on this artificial new type of text, we learn in fact the embeddings for the subject object and indirect objects of the verbs. I will not report any results here, but it's really improved the situation. And okay, so I will stop here. Having integration of the language resources and working on the, in fact, this has at least two advantages. One is that we really have the resources and can train also models, different models on it. but also we can use them to generate better artificial text in order to improve the word embedding. And I think I'll stop here. Thank you. Okay, so questions if there is. Let's go silly.
Maybe we can switch questions actually to offline part,
Okay.
because we will have
It's already late.
them quite soon, so.
Right. So we'll switch the questions to the offline part. Thanks everybody for being here. Bye-bye to the users at home, and we'll continue the questions and discussion here in Kaunas on site. So once again, a reminder, see you all in Klaipėda on the 20th of May, and have a good evening. Bye-bye.